again in our series on numerical methods in engineering. Recall last time we talked about iterative methods for overdetermined linear systems. What are overdetermined linear systems? Where there's a coefficient matrix A which has size m by n, where m is greater than n. Basically, we have more equations than unknowns. We have more equations than unknowns. So those are what are known as overdetermined linear systems. So for instance, an example of an overdetermined linear system is when we want to find the least square solution to a problem Ax is equal to b. So we want to find the solution x, which is the best solution in some norm. For instance, for the least square solution, we want to find the solution which gives the minimum residual in the L2 norm, right? We want to find x such that r is equal to b minus x is minimum, and minimum in the L2 norm. And we also recall that the residual, which if we minimize a function and minimize the residual, the L2 norm of the residual, we find an x, and we also find a residual which is equal to b minus ax, and the residual is orthogonal to the space spanned by the column vectors of A. To the vector space spanned by the column vectors of A, the residual is orthogonal to that space, or A transpose R is equal to 0, right. So the residual basically projects out the component. It is basically the component left after projecting B onto the space which is spanned by the column vectors of A. And the solution also satisfies, we also recall this condition, this relationship, A transpose A x is equal to A transpose B. And if A has full rank, we found last time that A transpose A is always going to have full rank 2, that is A transpose A is also always going to have a positive determinant, it is going to be non-singular. So by solving this equation, by inverting A transpose A, we can find out our least square solution x. However, problems arise when A transpose A is ill-conditioned or singular. If it is ill-conditioned, we cannot invert it with appropriate levels of accuracy, and if it is singular, we cannot invert it at all. In that case, we said that the proper way to go about doing this problem is probably to do a QR decomposition. A QR decomposition, which says there is the QR theorem, which says that let A be an m by n matrix with m greater than or equal to n and linearly independent columns, then there exists a unique m by n orthogonal matrix Q such that Q transpose Q is another diagonal matrix D with all positive entries, and a unique upper triangular matrix R with 1 on all the diagonals, right, a unit upper triangular matrix R. So A is equal to QR, where Q is an orthogonal matrix and R is a unit upper triangular matrix. It is clear that a QR decomposition with the stated properties exists only when A has full rank. Why is that? Because we have said that A has n linearly independent columns, right. So if it has n linearly independent columns, it's got to have full rank. So the QR decomposition assumes that A has full rank, thus it is applicable if A is non-singular, but A transpose A is ill-conditioned. So it is directly applicable to the case where A transpose A is ill-conditioned, so that A transpose A is prone to numerical errors. However, even if A is singular, that is A does not have all linearly independent columns, we can use a modified form of the QR decomposition to find the least squares solution. Let us first consider the case where A has full rank. So using QR decomposition, we can replace A transpose by R transpose Q transpose. R transpose Q transpose B minus Ax must be equal to 0. And since R is non-singular, recall R is a unit upper triangular matrix and also recall that an upper triangular matrix, the determinant is given by the product of its diagonal terms, and since all its diagonal terms is 1, it is evident that this R must be non-singular. So, since R is a non-singular upper triangular matrix, we know that R is invertible. So, this equation is effectively becomes Q transpose B minus AX, right, because R is also always invertible. So, Q transpose B minus AX is equal to 0, implies Q transpose B is equal to Q transpose AX, or Q transpose AX is again equal to Q transpose QR using the QR decomposition, Q transpose QRX, Q transpose Q is equal to the diagonal matrix D. So, Q transpose B is equal to DRX. Hence, to find X, we have to solve this system, we have to invert this product dr, and we get X is equal to R inverse D inverse Q transpose B. The above equation is solved in 2 steps. Recall, whenever we do operations with triangular matrices or with both upper triangular and lower triangular matrices, which we found when we did our LU decomposition while doing Gaussian elimination, it always sometimes makes sense to do this problem in 2 steps. But in order to do this problem in 2 steps, we have to define an intermediate vector y is equal to D inverse Q transpose B. So, basically we define an intermediate vector comprising these terms, right, D inverse Q transpose B, and then we calculate, and then we solve Rx is equal to y. So, if Q and R is known, the least square solution can be found by solving the triangular system Rx is equal to y, of course assuming that we have already found the intermediate vector y from this operation D inverse Q transpose B. So, again this is a typo, this is not a capital B, this is because that is not a matrix, that is a vector, right. So, this is D inverse y equal to D inverse Q transpose the vector B, which is the right hand side of my system of equations. How do we find the matrices Q and R? Basically, this is a good time to introduce what is known as the method of Gram-Schmidt orthogonalization. So, Q and R are found using a modified Gram-Schmidt method. Since A has full rank, it is possible to construct an orthogonal matrix by computing a sequence A1, A2, A3 and so on up till An until we get the orthogonal matrix Q, where AK has the form AK is equal to Q1, Q2, Qk minus 1 and so on and so forth. So, basically let me try to explain the idea in words first. Basically, we start with the initial matrix A and we change one column at a time until we get an orthogonal matrix. To start with, so from A we transform A into Q. So, how do we do it? We do one column at a time. So, first we form the first column of Q. What is the first column of Q? The first column of A, right. But then at the same time we make sure that the remaining columns of A are orthogonal to the first column of Q. How do we do that? Well, we do that by orthogonalizing the remaining columns of A with my chosen first column, which is Q, and we go on and we continue in this fashion. So, the first k, so if we look at this here we are assuming that we have done up to k minus 1, right. So, we have formed the Qk minus 1, the k minus 1 columns of Q, and then we are trying to form the kth column of Q. So, how are we going to do that? Well, what we are going to do is that we will make the AK vector Qk. So, this AKK vector, right, this vector in the kth step, this vector is going to automatically become Qk. But in order to become Qk, we have to make sure that the remaining vectors AK plus 1 k through An k, they are orthogonal to the vector AK k. How are we going to do that? Well, we are going to do that by taking out the projection of AK with of qk, akk, which becomes qk from all these remaining vectors. So, at the same time that we make the vector akk qk, we orthogonalize ak plus 1 through an with respect to ak, such that aik plus 1 dotted with akk is equal to 0. So, that all these vectors, so now after orthogonalization ak plus 1 k becomes ak plus 1 k plus 1, because that is now for the next iterate, right. But how does ak plus 1 k change to ak plus k plus 1? For orthogonalizing it with respect to my new qk, which is actually akk. So, this automatically ensures that each qk is orthogonal to all the existing qi. So, basically let me go over it again. So, we start with the first vector of A, the first column vector of A, and make it the first column vector of Q. But in order to do that, I have to make sure that all the remaining column vectors of A are orthogonal to that Q. How are we going to do that? From each of those column vectors, remaining column vectors, I am going to project out the component of Q, right. So, if my second column vector is A2, right, I am going to compute my new A2 by A2 minus A2 dotted with the unit vector in the qk direction. So, I am just projecting out from A2 the part which lies along Q. So, simultaneously as I compute my orthogonal vectors, simultaneously as I compute my Q's, I also compute the kth row of my upper triangular matrix R. The steps of the algorithm are as follows. Suppose in the kth step, first thing that we do is we make the akth column of A the qk vector, right. Then from all the remaining columns of A, from j is equal to k plus 1 through n, for all the remaining columns, I project out the component of that vector along the qk vector, and of course, I normalize it by the magnitude of the qk vector, right. So, this makes sure that all my remaining column vectors after my kth vector, right, they are all orthogonal to all the previous qk vectors that have been formed until now. So, next time in the next iteration, I can automatically take the first vector and make it my next qk vector, because I am assured that all those vectors are orthogonal to my previously formed qk vectors. So, at the same time we compute R, which is nothing but Rkj is equal to qk dotted with ajk divided by dk. So, this is how we form our QR decomposition. So, we start with a matrix A, which is m by n, and then we step by step we orthogonalize that matrix, make each column orthogonal to each of the remaining other columns. We do it systematically using Gram-Schmidt orthogonalization. We are going to end up with an orthogonal matrix Q and a upper triangular matrix R. At the same time, we also compute the residual vector as the sequence B1, B1, we said B1 equal to B, B2, B3, Bn. As we compute each additional column of Q, we also change our right hand side B, so that at the end we are going to be left with the residual vector R, because during each iteration we are also projecting out from B. We start with B0, B1 equal to B, and each step we project out from B its component in the current qk vector direction. So, we start with my original right hand side. At each iteration, at each step in my QR algorithm, I project out from my right hand side the component, the projection of the right hand side in the current qk vector direction. So, at the end I am left with whatever is left is going to be orthogonal to all the qk vectors. Basically, since all the qk vectors span my space A, so that means my residual is going to end up orthogonal to the space spanned by the column vectors of A. So, this is how I compute Bk plus 1, which is Bk minus Yk Qk, where I have defined Yk is equal to Qk dotted with Bk divided by Qk dotted with Qk. Since the vectors Qk will form a basis for Ra, this ensures that Bn plus 1 will be orthogonal to Ra. Do you recall what is Ra? It is the vector space spanned by all the column vectors of A. So, since we have ensured that the Bn are orthogonal to all the Qk's, we will ensure that at the end my Bn plus 1 is orthogonal to all the column vectors of A, and therefore, what is that? That is the residual. To compute the least squares approximation, we also need to obtain in addition the intermediate vector y. Recall, we need to compute the intermediate vector y, which we define to be y equal to d inverse q transpose b, and during the QR process we also compute y like this. Y is equal to q dotted with bk divided by qk dotted with qk. Recall that y is equal to d inverse q transpose b. So, this is basically that part, q transpose b, and then we are dividing by qk dotted with qk. This is this d inverse, that operation, right. So, once we have obtained q, q1, q2, qn, so all these columns which are orthogonal to each other, right, and we have obtained our right upper triangular matrix R, and we have obtained our vector intermediate vectors y, we solve for the least square solution using Rx is equal to y. So, this is what we can do when A transpose A is ill conditioned. We can of course use it when A transpose A is well conditioned also, but it is particularly suited for when it is ill conditioned, because then the normal method is going to break down. What happens when instead of being ill conditioned it is actually singular? That is, A transpose A is actually singular because A does not have full rank. What happens then? In that case, the normal QR procedure is going to break down. How is this going to happen? We can see it as follows. We know from the QR decomposition Q is equal to AR inverse, right? Q is equal to A is equal to QR, so Q is equal to AR inverse. Let us denote R inverse is equal to S, an upper triangular matrix. We are assuming that since R is an upper it's true, it's not assuming, it's you have to take me on trust now, but it is true that since R is an upper triangular matrix, R inverse is also going to be an upper triangular matrix, and it's also going to be a unit upper triangular matrix, right. So, we can write Q is equal to A times S, A product S, matrix product S. Then the kth column of Q can be written as Q is equal to AS. So, the kth column of Q is nothing but Q1k, the kth column, all the entries in the kth column, Q1k, Q2k through Qmk, which is going to be nothing but A, the first row of A multiplied with the kth row of S, right. So, this is the first row times the kth row of S, second row times the kth row of S, mth row of K A times the kth row of S. So, this gives me the kth column of Q. So, we can write this concisely as Qk is equal to some scalar times the first column of A, right, plus another scalar S2k times the second column of A, plus another scalar Sk minus 1k this time times the mth column of this is the k minus 1th column of A, and finally we are going to have A1k, right. Why is there nothing here? Because it is a unit triangular matrix, right. So, Skk is going to be 1, right. So, Sk minus 1k, Skk is going to be 1 because it is a unit triangular matrix. So, we can write each Qk as a linear combination of the A vectors of the columns of the A matrix A1, A2, A3 up to A. So, again this is a typo, this should be AK minus 1 plus AK, right. So, it is clear that each QK is a linear combination of the columns of A1, A2 through AK. Since let us suppose that A1, A2 through AK minus 1 are linearly, recall now we are considering the case where A does not have full rank. What does that mean? That means that there are columns in A which are linear combinations of the other columns, right. Not all the columns of A are linearly independent, right. A does not have full rank. So, let us assume that the kth column, that the kth column of A is a linear combination of the first k minus 1 columns, right. Since it is a linear combination of the first k minus 1 columns, and we have just shown that each qk is a linear combination of the all the previous k columns. So, that means that AK is also a linear combination of all the Q1 through Qk minus 1. Thus, during the QR procedure, we are sure to get AKK is equal to 0 and the orthogonalization was going to break down. Why is that? Because recall, at each step, as each time we form a new Q vector, we orthogonalize all the remaining vectors with respect to that vector. So, we project out from each remaining vector the Qk vectors that have been formed previously. Now, since AK is a linear combination of all of the k minus 1 previous k minus 1 columns of A, when we project out from AK the k minus 1 previous k minus 1 columns, we are going to get 0, because AK is basically a linear combination of the k minus 1 columns, right. So, eventually we are going to land up with an AK which is 0, and when we do that, our orthogonalization procedure breaks down, because the QR procedure depends on making the first column, the first of the remaining columns, the next Qk vector. But the first of the remaining columns is now AK, but AK is identically equal to 0. So, our algorithm is going to break down. But however, if the rank of k is greater than k, up till now we have formed k minus 1 independent columns, but suppose the rank of A is more than k minus 1. If the rank of A is just k minus 1, well, that is it, we can't go any further, all the remaining columns are sure to be 0, right, because they have been all orthogonalized with respect to the previous k minus 1 columns, right. But if the rank is greater than k minus 1, there are still some columns which are non-zero, right. There are still some columns of A which are non-zero. So, what we do? We do a pivoting, we do a column interchange. We replace the k, suppose the jth column is not 0, and where j is greater than k but lesser than or equal to m. We can then interchange the columns k and j and proceed until all the remaining columns are linearly independent on the computed k vectors. So, we keep on doing this, we keep on interchanging until we reach a situation when all the remaining columns are orthogonal to the computed q vectors, which means that all the remaining columns are 0, right. So, a systematic way of doing this would involve column pivoting. At each step, we would choose S as the smallest integer for which ASK is equal to max of AJK, j varying from k to n, and then interchange the columns k and s. Basically, we at each step, instead of just directly taking the next column and making it the q vector, we look at all the remaining columns and choose the column which has the maximum norm in the infinite sense, right, infinite norm, right. This is the maximum infinite norm, make that the q vector, and so on and so forth, right. So, if rank of A is suppose R, which is less than n, we can therefore be assured of forming the orthogonal matrix of dimension m by r, that is q is equal to q1, q2 through qr. So, we can form R, since it has rank R, we can form R orthogonal vectors, right. We can form R orthogonal vectors, q is of size m cross r. During the reduced orthogonalization process, we also form the reduced upper triangular matrix R, which has dimension R by n and the vector y with length r, using the same procedure that we talked about earlier. So, we are also forming the r and the y vectors. We separate R into two parts, R prime and S prime, with R prime of size R by R. Remember that Q is of size M by R. So, R must be of size R by N, because A is of size M by N, right. So, M by N is equal to M by R product with R by M. So, now so basically we are saying that we are going to split R into two parts, R prime and S prime, R prime of size R by R and S prime of size R by R n minus R. Similarly, the unknown solution vector x is separated into R and n minus R components. We separate out the first R components of x like this as x1 and the R plus 1 to the nth component as x2. Then we can write Rx is equal to y, such that now see we have split up R into two parts, R prime which is of size R by R and S prime which is of size R n minus R. Similarly, we have split up this vector into this little part x1 which is of size R and this part x2 which is of size n minus R, right. So, R prime x1 plus x prime x2 must be equal to R, which gives me x1. I can write it as R prime inverse y minus R prime inverse S prime x2. These x2 are arbitrary, right, because my matrix has, my A matrix has got rank R, right. So, we have to assume x2 arbitrary values, x2 arbitrary. Remember, anytime we have less than full rank, we are going to have infinitely many solutions, right, infinitely many solutions, and we have to assume as many solutions as the null space, right. In this case, the null space is of size n minus R, right. So, x2 is of size n minus R. These are arbitrary values, and I can write my remaining x1 in terms of this x2, right, and my y which I formed during my orthogonalization. So, assuming arbitrary values of x2, the first R components of x can be determined from this expression, the x1 components. Similarly, if we take x2 is equal to 0, since x2 is arbitrary, we can take any value. If we put x2 is equal to 0, we get x1 is equal to R inverse y. So, this equation gives the general least square solution for the situation where the coefficient matrix is singular and of rank R, right. So, there are infinitely many, recall now, there are infinitely many least square solution now, right. Why? Because my x2 are arbitrary, right. Those n minus R components of x are arbitrary. I can make them 0, I can make them anything I like, right. But they all satisfy the least square solution. So, they all minimize the residual. They all minimize the residual, they all satisfy the least square criteria. So, there are infinitely many least square solution to the problem, right. Unlike the case when A transpose A was non-singular, where we had only one solution, in this case there are infinitely many least square solutions, but in all of them make sure that the residual is, all of them make sure that the residual is orthogonal to the space spanned by the columns of A. In this case, the space spanned by the columns of Q. So, this is just a diversion, but if during the orthogonalization procedure, instead of setting Qk is equal to Akk, we in addition to orthogonalizing, we also normalize, right, we orthonormalize sort of. So, we set the Qk vectors so that each of them have norm 1. So, not only they are orthogonal to each other, they have unit norm also. Then we are assured that my Q matrix is, again this is a typo, assured the columns of Q being ortho, I apologize, this is Q, right. The columns of Q are orthonormal, right. In that case, Q transpose Q is going to be the identity matrix. So, D is equal to the identity matrix, and in that case A transpose A can be written as R transpose QR, which is equal to R transpose R. We have encountered this decomposition before when we talked about the Cholesky method, right. So, this QR decomposition gives the triangular matrix R as in Cholesky's method. So, in case we in addition to orthogonalizing Q, we normalize the columns of Q, we get a we recover the Cholesky's method. This normalized decomposition, QR decomposition, has the same disadvantage as Cholesky's method. It is computationally expensive, requiring the evaluation of square roots, which we found in case of Cholesky's method. As soon as we have R transpose R, there are going to be square terms and we have to evaluate square roots. So, it becomes computationally expensive. Okay. So, that was a discussion on overdetermined linear systems, the QR decomposition to solve the overdetermined linear system. The QR decomposition is a very important tool in numerical methods. So, it is not only its usefulness is not restricted to overdetermined linear systems, it can be used, it has got lots of other uses. It can be actually used to find, it is probably very powerful tool for finding eigenvalues also, although we will not talk in great detail about the use of QR in finding eigenvalues, but it is a very useful tool in finding eigenvalues also. So, it is a very important and powerful tool. But next let us switch over to finding out how can we calculate how can we solve the eigenvalue problem. Basically, if we are given an n by n matrix and we are interested in finding its eigenvalues and eigenvectors, how can we solve it? If it is a small matrix, if it is a 2 by 2, if it is a 3 by 3, if it is a 4 by 4 probably matrix, we can do it by hand. We can set up the characteristic equation and solve it, right. But in case we have very large matrices, then solving that problem becomes difficult. It requires very sophisticated numerical methods, and I can assure you that solving eigenvalue problems are essential if we are going to do any reasonable numerical solution. For instance, if you want to do stability analysis, you need to find eigenvalues. There are countless other applications where eigenvalues are very important. So, eigenvalues and eigenvectors are crucial parameters for fully characterizing a linear system. For direct solution of Ax is equal to B, we know that since the eigenvectors of A, if linearly independent, form a basis for the solution space, we can use the eigenvectors to solve the problem, right. Again, for stationary iterative methods, which we have encountered just a little while ago, we found that the whole stability of the method depends on the eigenvalues of my B matrix, right, which was my iteration matrix, right. So, the eigenvalues of that B matrix determine whether my iteration method is going to be stable or not. After I do n iterations, whether I am going to converge to a solution or I am going to divert and go somewhere totally different, right. So, that all that depends on my on the spectrum of my B matrix, right. Thus, it is very important in numerical analysis to be able to determine the eigenvalues and eigenvectors of a matrix. The eigenvalues lambda I and the eigenvectors x of an n by n matrix satisfy the relation A minus lambda I xi is equal to 0, provided that xi is not equal to 0. If we know the eigenvectors, we can find the eigenvalues trivially. We just compute A is equal to lambda I x. So, xi transpose A xi, xi transpose A xi, divide xi transpose A xi, xi transpose xi, we get my eigenvalue, right. So, that can be done trivially provided the eigenvectors are known. However, that is not so easy. Finding the eigenvectors is not so easy. So, we have to find ways of finding the typically the eigenvalues are found first and simultaneously eigenvectors are found. Typically, we do not know the eigenvectors a priori beforehand. So, we know that for this system, this is a homogeneous system. For it to have a non-trivial solution, meaning that for not all xi, all components of xi to be not equal to 0, then the determinant of a minus lambda I must be equal to 0. On expansion, we get a polynomial of degree n. So, if it is a 3 by 3 matrix, we get a polynomial in a third degree cubic equation in lambda. If it is a 2 by 2 matrix, we get a quadratic equation in lambda. If it is a 4 by 4 matrix, we get a quartic equation in lambda. So, we get a polynomial of degree n whose n roots are the eigenvalues of the system. This polynomial is known as the characteristic polynomial. Again, there is a theorem which is known as Abel's theorem, which tells us that it is not possible to obtain analytically the roots of a polynomial of order greater than 4. So, if this polynomial becomes greater than 4, if it is a 5 by 5 matrix, I have a quintic polynomial, right. I have lambda to the power 5. In that case, there is Abel's theorem, which tells me that you cannot find the roots of this polynomial using any analytical method, however hard you try, right. So, the only way you can find the roots of that equation are through numerical methods, right. So, one possible method is to determine the coefficients of the characteristic polynomial Pa lambda, which is like this, lambda to the power n, lambda to the power n minus 1, and so on, and then solve it by some numerical method for algebraic equations. Why numerical methods? Because for orders greater than 4, we cannot use analytical methods, and even for orders less than 4, it is not a good idea sometimes to use analytical methods. I will talk about the reasons just now. The coefficients of Pa are very sensitive to minor perturbations. So, if you have your original matrix A and I give minor perturbation to the elements of A, so we add to A matrix epsilon times B, where epsilon is a very small number. So, I give perturbations to A. So, you expect the eigenvalues of A to change by epsilon, right, because I have changed the components of A by epsilon. So, I would expect that the eigenvalues of A would also change slightly by epsilon, but it does not happen like that. Why is that? Because the coefficients of my characteristic equation are very sensitive to minor perturbations, right. So, they are not very well conditioned, right. Minor perturbations in A result in large changes in the roots of my polynomial, of my characteristic equation. Thus, minor perturbations, the elements of A, which should cause minor differences in the eigenvalues, cause large, again there is a typo, large differences in the roots of Pa lambda. Thus, this is not a practical approach until the matrix A is a very low order and has well separated eigenvalues and has well separated if A is of low order and has well separated eigenvalues, then this is fine. However, otherwise we need to think of alternative methods for determining the eigenvalues. So, before talking about the alternative methods for determining eigenvalues, I want to talk about an important theorem in linear algebra, which is known as Gershgorin theorem, which is very useful, although it is not as useful as one would like to hope, but it is also useful because because it allows us to determine bounds on the eigenvalues. Recall our stability criteria. What was our stability criteria for our Jacobi's method or for Gauss-Seidel's method? The stability criteria was that the spectral radius must be less than 1, which means that my largest eigenvalue must have magnitude, must have norm less than 1. So, this Gershgorin theorem allows us, even before actually computing the eigenvalues, to find out bounds on the eigenvalues. It tells me what can be the maximum possible eigenvalue of this matrix. Given a matrix, without actually computing my eigenvalues, by using Gershgorin's theorem, I can find out what can be the maximum absolute value beyond which will never be exceeded by the eigenvalue of that matrix, right. So, so that allows us to get some idea of the stability of the system even before computing the eigenvalues. It allows us to get a priori estimates of the stability of the system, which are useful, but not so useful, because the bounds predicted by Gershgorin's theorem are so wide, right. So, they are, so if my eigenvalue is 5 suppose, and Gershgorin's theorem tells me that the eigenvalue will never exceed the value 500, that bound is not very useful, right, but it is still useful sometimes, but it is a very wide bound. So, narrow bounds are more useful than wide bounds, right. So, let us look at Gershgorin's theorem. A theorem due to Gershgorin provides a bound on the eigenvalue of a matrix. It states that let A be an n by n matrix with eigenvalues lambda 1, lambda I is equal to n, then each lambda I lies in the union of the circles formed like that. So, what does this mean? It means that if I form a circle with center, I form a series of circles, right, and each circle, circle 1 for instance, has center with diagonal element A11, right. It has a center with diagonal element A11, and it has got radius which is sum of the absolute values of all the non-diagonal elements in that row, right. Since I am looking at the first row, Ri, the radius of that circle, is sum of all the non-diagonal elements in the first row. So, it tells me that if I compute circles like this, right. So, I look at the first row, look at its diagonal element, make that the center of my circle, and draw a circle with a radius which is equal to the sum of the norm of my off diagonal elements. I do that for the second row, again draw a circle with centered at the diagonal term and radius equal to sum of the absolute values of the diagonal elements. I go on doing this. Then if the union of all these circles, right, the union of all these circles defines my Gershgorin bound. So, if I draw this series of circles and then I draw a circle which circumscribes all these circles, which is basically the union of all these circles, union of all those circles, the eigenvalue will lie within that circle. The eigenvalue cannot lie beyond that circle, the maximum eigenvalue cannot lie beyond that circle. This can be proved as follows. Let lambda be an eigenvalue of A, then there is eigenvector of x not equal to 0 such that Ax is equal to lambda x, right. Hence, we can write lambda minus Aii xi is equal to Aij xj. So, basically I have kept the diagonal term on the left hand side and I have moved all the off diagonal terms to the right hand side. So, let us consider, so if I do that, I can do that for each of my equations I equal to 1 through n, assuming that A is a matrix of size n by n. So, I can do it for each of those rows. Next, let us consider the equation I corresponding to the component of x with the largest absolute value, right. So, let us consider ith row such that the ith row x has the maximum maximum absolute value, right. In that case, for that row I can write mod of lambda minus Aii xi is equal to sigma mod of Aij xj. So, basically I am just taking mod of both sides, right. I am taking mod of both sides in this equation, and mod of sum of Aij xj I can write is going to be lesser than or equal to sum of mod of Aij xj. We have seen this many times before, and dividing throughout by mod of xi. So, we divide throughout both sides by mod of xi. So, mod of lambda minus Aii xi divided by mod of xi is going to give me mod of lambda minus Aii. This is going to be lesser than or equal to mod of Aij xj by mod of xi summed from j equal to 1 to nj not equal to I, which is going to be lesser than or equal to sum of mod of Aij. Why? Because we have chosen I to be the largest component in the x vector. So, all the xj's, and these j's are spanning from j equal to 1 to nj not equal to I. So all these xj's are going to be less than xi. So this is going to be less than 1. This factor mod of xj by mod of xi is going to be less than 1. So this is going to be less than mod of aij, which is equal to ri, right. So for the row which corresponds to the largest absolute value of x, this is true, right. This is true for that row. Thus, the largest eigenvalue lies on or within the union of all circles with centers at the diagonal elements of the coefficient matrix A and with the radius as given above. This is slightly you have to use your imagination. Basically, we are looking for the row which has the largest entry in x. This is true, right, but we do not know a priori what is my row with the largest entry of x, right. I do not know what are my eigenvectors. So how do I know which is going to be my row in the eigenvector with the largest entry of x? So I have to assume that any of those rows in x can be the row with the largest entry, and I have to compute this circle and the radius for each of those rows, right, and the union of all those circles is going to give me my upper bound, right. Is that clear? So the bound above says that the eigenvalue will lie on or within a circle centered on the diagonal element corresponding to the largest entry in a given eigenvector xi. However, we have no way of knowing a priori the location of the entry with the largest magnitude for a certain eigenvector, since the eigenvector itself is unknown. Hence, it is necessary to take the union of all. So we have to take all the rows, right. We have to take the union of all the circles centered about each diagonal element with the radius comprising the sum of the absolute values of diagonal elements. So that was Gershgorin's theorem. So let us use Gershgorin theorems to look at stability of the eigenvalues. Let us consider effect of perturbations in the elements of a matrix on its eigenvalues, denoting the perturbed matrix as A epsilon is equal to A plus epsilon b. So I have my original matrix. I apply some perturbation on the elements of the original matrix by scaling a matrix B with a very small number epsilon and adding it to my matrix A. So I want to know, if I know my eigenvalues of A, what does this tell me about the eigenvalues of A epsilon, which is A plus epsilon b? First, let us assume that A has linearly independent eigenvectors. So the matrix X is non-singular. What is the matrix X? Since xi are the eigenvectors and lambda I are the eigenvalues of A, we can write the equations Axi equal to lambda I as A operating on X. X comprises columns, n columns, each column being an eigenvector of A. So A operating on X is equal to X operating on lambda, right. Basically, we are writing all the eigenvalue equations together, right. So we are creating a matrix X, each column of which is an eigenvector, and we are creating a matrix lambda which is a diagonal matrix, and each diagonal matrix is an eigenvector. So we can write it like this. And since A has linearly independent eigenvectors, the matrix X has full rank, because each of its columns is an eigenvector, and each eigenvector is linearly independent. So X has got full rank. X is invertible, right. X is non-singular. So we can define a matrix C is equal to X inverse Bx, so that we can write X inverse Ax. So we are operating on X with A, right, and then operating on the resultant with X inverse. So X inverse Ax is going to be X inverse Ax, right, this part, plus epsilon X inverse Bx. But X inverse Ax is from this, X inverse Ax is nothing but lambda, right. X inverse Ax is going to give me my diagonal matrix lambda. So lambda plus epsilon x inverse bx, and I defined x inverse bx is equal to c. So, x inverse ax is equal to lambda plus epsilon c. Suppose x inverse ax has got eigenvalues lambda star and eigenvectors x star. So, we are now writing the eigenvalue problem for x inverse ax, a epsilon x, and we are saying that suppose x inverse a epsilon x has eigenvectors x star and eigenvalues lambda star. Then ax xi is equal to lambda star x xi. So, basically we are bringing this x to the right hand side, right, lambda star x xi, and we have a epsilon x xi, right. So, if we denote x xi bar xi star as x bar, we have a x bar is equal to lambda star x bar. So, what does this mean? This means that a epsilon has the same eigenvalues as x inverse ax, x inverse a epsilon x, right? Why? Because the eigenvalues of x inverse a epsilon x are lambda star, and we have just proved that the eigenvalues of a epsilon are also lambda star. Thus, a epsilon has the same eigenvalues of a x inverse a epsilon x, and the eigenvectors of a epsilon are related to the eigenvectors of x inverse ax by this operation, eigenvectors of x inverse ax by this operation x xi star. So, if I have an eigenvector of x inverse ax, if I operate that with this matrix X, I am going to get an eigenvector of a epsilon. Hence, using Gershgorin's theorem on star, basically I am going to use Gershgorin's theorem on this equation. And what does Gershgorin's theorem tell us? It tells us that the largest eigenvalue of this matrix, right, satisfies this bound, right, lambda I minus diagonal element of this matrix, right, must be lesser than or equal to sum of the off diagonal terms, right. It has to satisfy this equation from Gershgorin's theorem, diagonal minus off diagonal, from which lambda I epsilon, which is this, right, lambda I epsilon. Why do we write lambda I epsilon? Because we know that lambda I of a, lambda I is nothing but the eigenvalues of a epsilon. We know that the eigenvalues of a epsilon are the same as the eigenvalues of x inverse a epsilon x, right. So, lambda I a epsilon is equal minus lambda I epsilon ci. Why do we do that? Well, because recall that x inverse ax is equal to lambda plus epsilon c, where lambda is the eigenvalues of my original A matrix and epsilon c, where c I defined like this, right. So, we can write this as lambda I minus epsilon cii, because this is basically the eigenvalue of the diagonal term of this matrix, right, and this must be lesser than or equal to sum of the off diagonal terms, which is equal to epsilon cij, right, because again let us go back again, the off this matrix is diagonal, right. So, all the off diagonal terms of x inverse ax are given by epsilon c, right. So, we have this must be lesser than or equal to epsilon mod of cij, which implies lambda I epsilon minus lambda I must be of order epsilon. So, these terms are of order epsilon. So, difference between lambda I epsilon and lambda I must be of order epsilon. So, what does that mean? This means that my eigenvalues of my perturbed matrix lambda I epsilon are different from the eigenvalues of my original matrix by order epsilon, right. So, they are of the same order as the perturbations, right. So, if A is a symmetric matrix, then X is an orthogonal matrix, and we can choose X to be an orthonormal matrix by normalizing each eigenvector. Thus, the elements of C x inverse Bx are of the same magnitude as B. Why? Because C is equal to x inverse Bx, components of the columns of A each of x each have norm 1, unit norm. So, x inverse, the magnitude norm of x inverse Bx of C must be of the same order as B, because these things have, each column has unit norm, right. So, C has to have the same norm as, must be of the same order as B. So, the eigenvalues of the perturb system are bounded by the perturbations in A. Hence, the eigenvalue problem of a symmetric matrix is always well conditioned. Why do we say it is well conditioned? Because I have applied perturbations to A, right, small perturbations epsilon times B, but that has not changed my eigenvalue by a large amount. It has only changed it by order epsilon, by the order of the whatever perturbations I applied, right. So, that means that the problem is well conditioned. That is the definition of a well conditioned problem. A minor change in the input values does not result in large differences in the solution. So, minor change in my A matrix does not change my eigenvalues significantly. So, we will continue our discussion on eigenvalues next class, next lecture. Thank you very much.